All right, welcome to another exciting episode of SchmidtChem. We're looking at this year Kinetics Quiz number one. Consider the following reaction: a 100 milliliter flask at 25 degrees Celsius is charged with 0.1 moles of N2 and allowed to react with 0.3 moles of H2 according to the reaction above. So here we're supposed to write a rate expression. This is not a rate law, but it is a rate expression. And we know what we're supposed to do when it says in terms of appearance and disappearance. This is what these look like. They do not look like rate laws in which we are putting the order of the reaction in there, but we are just simply relating the change of the reactants to the products, the rate of change of in the concentration of the reactants of each of the reactants to the rate of change of each of the products. And so that will look like rate is equal to, now we notice that N2 is a reactant. We know that we put a negative sign there because it is disappearing, meaning it is being converted to something else. And so the change of N2, or the change in the concentration of N2, will be negative. And if we don't have a negative sign in our expression, well, then the rate would be negative, and the rate cannot be negative. So we have to put the negative sign into our expression to account for that. And that is then going to be the change in N2 with regard to the change in time. Then we also know that the rate of the reaction is going to be equal for each of the reactants. We're not going to have the rate be faster. The rate of the reaction is not going to be faster because of H2 than it is for N2, because these are all working together to establish the rate. However, the change in concentration with regard to time is different for each of these based off of the stoichiometry. We can see that it takes 1 mole to react of N2 to react with 3 moles of H2. That means the change in concentration of H2 over the same amount of time is 3 times greater than what happens with the change in N2. And so that the rates are the same, we have to account for this coefficient here. And we do so by taking the reciprocal of the coefficient. Now, here we're going to still make that negative. So that's still going to be negative, but it's going to be negative 1/3 the change in the concentration of H2 with regard to the change in time. And then we're going to do the same thing for NH3, except for NH3 is a product. And so we're going to put 1/2 the change in the concentration of NH3 with regard to the change in time. All right, and so that's what that is there. And just to make sure that is a clear bracket, there we go. We'll go and do that. All right, so that's how we write our rate expressions in terms of appearance and disappearance of each of the products and reactants. All right, and so now we're looking at the concentration initially, or at time 0. We see that the moles of N2 is 0.1. We see that the volume of the flask is 100 milliliters. So we know that from our resource sheet that molarity is equal to moles per liter, and that is going to be 0.100 moles for every 0.100 liter, 100 milliliters being 0.1 liter. We cannot put 100 milliliters in here. We have to convert that to liters because concentration is moles per liter, not moles per milliliter. And so 0.1 divided by 0.1 is 1 molar. This is of N2. Now we find that at 160 seconds. So we go to our table and we see that at 160 seconds, again, our formula is molarity is equal to moles per liter, or N over L. And what we see is that we have 0.020 moles for every 0.100 liter. This will give us 0.2 molar of N2. All right, and that's that. Now, we want to calculate the average rate of the reaction between time 0 and 160. But we only have data for N2, and good thing is we have a rate expression for that as well. So we can use our rate expression to determine the average rate of the reaction. So rate is going to be equal. We just plug in our expression for N2 because that's what we have data for. And then we solve. And so this is going to be negative. We know the change is always final minus initial, so it's going to be 0.2 molar minus 1.0 molar over 160 seconds. All right. And so what we see is 0.2 minus 1 divided by 160, and we should get 0.005 molar per second. Notice the units molar per second. And then notice it's a positive value. This change here would have been negative, but we multiplied it by a negative sign to account for that, so that the rate of the reaction is going to be 0.005 molar per second. All right, so now we're supposed to use a rate expression to calculate the rate of change in concentration of NH3 that occurred between 0 and 160 seconds. So if we look at NH3, our expression is 1/2, rate equals 1/2 the change in concentration NH3 with regard to time. So rate is equal to 1/2 the change in concentration of NH3 with regard to the change in time. What this is asking us for is to find the rate of change in concentration of NH3. And so what we're looking for in particular, to make it very clear, is this. It's not a highlighter. So let's do this. Is this value right here? All right. And so we're going to solve our equation for that expression right there. So this is going to be the change in the concentration of NH3 regarded with the change in time is going to be equal. This is the rate of change in the concentration of NH3. This expression that gives us the rate of the change in the concentration of NH3 is going to be equal to the rate of the reaction times 2. And so we know that we have the rate of the reaction, or average rate of the reaction, is 0.005 molar per second times 2. And that's going to be 0.01 molar per second. And so this is our answer. All right, and that was our answer. And that was our answer. And that was our answer. Okay, so now we want to know, what is the concentration of NH3 after 160 seconds? We know the average rate of change of NH3 that occurred between 0 and 160 seconds, but now we want to know, what is the change in the concentration? So what we're going to do then is we're going to start with our time. Our time is 160 seconds. And then we know, according to part D, that 1 second is equal to 0.01 molar. And so we notice that seconds and seconds cancel, and we're left with the unit molar, right? Molarity, which is what we want to know. What is the concentration after that time? So we take that rate times 160, and it is 1.6 molar. So what is the concentration of NH3 after 160 seconds? It's 1.6 molar. All right. Now, use your answer in part E to calculate the number of moles of NH3 in the container at 160 seconds. All right. So now what we're supposed to do is figure out the number of moles. So, sorry, I got delayed there. So what we're going to do then is we're going to take solve for the use the concentration to solve for the number of moles. So we know the volume of the container is 0.1 liter, and we know that in molarity, what this expression actually means is 1.6 moles for every 1 liter. So we know that 1 liter is equal to 1.6 moles of NH3. If we want to be very specific. And so we take that and we get 0.16 moles of NH3. All right, and that's all there is to that. Okay, so we go to the next part, and it says to calculate the partial pressure of NH3 in the container at 160 seconds. So we know partial pressure of NH3 is going to be equal to, so again, we're using our gas law here, PV equals nRT. That's where we're getting this from. P is equal to nRT over V. Now we know the moles of NH3, 0.16 moles. According to our resource sheet, the R value is 0.08206. Get that decimal in there. Liters ATM over moles Kelvin. And then our temperature, we're going to have to go back to the top. Temperature was 25 degrees Celsius, 25 degrees Celsius. Now notice our units should be in Kelvin. So we're going to have to take 25 plus 273.15, and we get 298.15 Kelvin. All right, we take that over, what's our volume in the container? 0.1 liter. That has to be in liters because of the value of the constant. All right, and so we're going to plug these in. And so we have 0.16 times 0.08206 times 298.15, and then divided by 0.1. What we get is 39.14. What's the unit? You may wonder, what unit am I supposed to have? Well, moles is a numerator, moles is denominator, Kelvin numerator, Kelvin denominator, liters numerator, liters denominator. We're left with ATM, and that is a unit of pressure. And so that's how we get that. And so that's question number 1 of the quiz. All right, we go on to the next part, question number 2. And what we're looking at is this following reaction is studied, experimental data for the reaction is given, and we're supposed to calculate the order of the reaction with respect to ClO2. All right, and so what we're using here is the method of initial rates. Just in case you didn't know that, we see it says initial rates right here. So that's a big clue that we should be using that. So if we want to find the order with respect to ClO2, we have to look at experiments in which OH is not going to change. And so we see experiments 1 and experiments 2 that OH remains constant. However, ClO2 does change. And so that's what we're going to use then. So what we're going to want to do is we're going to look at the change in concentration. By what factor does the concentration change? So the change in concentration, and maybe I'll make that look a little bit clearer, but we're looking for a factor of change in concentration. And so this is going to be taking always the higher value divided by the lower value. It just makes it a little bit easier. So our concentration change in ClO2 is 0.060 over 0.020. Of course, we can put units here, but we know they're the same units, so they're going to cancel out. And so this is going to give us a value of 3, or it's going to, the concentration change by a factor of 3. Well, how did the rate change? So now we're going to have to plug these in. So notice we have 0.060 in the numerator. We have to use the rate for 0.60 in our numerator for rate. And so we're going to put 0.0248. Again, it's molar per second, but these are going to cancel out because both of these are going to be units of rate. And then we're going to divide it by 0.00275. And you notice it's the larger number in the numerator and the smaller number in the denominator. So 0.0248 divided by 0.00275. And what we end up with is somewhere approximately 9. So we see that the concentration changed by a factor of 3 and the rate changed by a factor of 9. So if we take 3 and we say to some power equals 9, we would say, oh, well, that is obviously 2. And so we know this is going to be second order. Or we can use our definition and say that the change in the rate is proportional to the square of the change in the concentration, which defines it as being second order. So this is second order. Second order. Or second order. However you want to say it. All right. Now we go to the next part, and it says calculate the order with respect to OH. So we go back and we look at our initial rates. Now we want to find experiments in which ClO2 does not change between experiments 2 and 3. So the change that we see in the rate here is due to the change in the concentration of OH only. And so we can see that this is a really good place to get our data. And so again, use the larger value over the smaller value. So we're going to look at the change in the concentration, and we see that it is going to be 0.090. Of course, that does have a unit, but these are going to cancel, over 0.030, and that is a factor of 3. Now we're going to look at the rate. Now we have to make sure we align these things appropriately. So we use 0.9 first in the numerator, so we're going to have to use this value in the numerator. So this is 0.00828. Of course, it's molar per second, but these are going to cancel, over 0.00275 molar per second. And so let's see what that change is. So we put in 0.00828 divided by 0.00275, and what we end up with is 3. And so we notice that, okay, we have a change in concentration of 3 to some power is going to give me 3. Well, n is equal to 1, or it's first order. Or we can use the definition and say that the change in concentration, the change in the rate is directly proportional to the change in concentration, which is defined as being first order. So this is first order, or you can say first order, however you want to say it, as long as it's first order or first order. All right. So we write the rate law for this reaction. So we want to write this rate law, and we want to say that it is going to be second order with regard to ClO2, and first order with regard to OH. So this is going to be rate is equal to, now notice this is rate law. This does not say write a rate expression that relates the change of one reactant to the other reactants and products. This is a rate law. And just so I have a little more room over here, I'm going to move it over here. It's going to be rate is equal to K, concentration of ClO2 squared, because it's second order, times concentration of OH minus, and I don't have to put the 1 there, but I did anyway. All right, and it's showing that it's first order. So the overall order is going to be, we can say it's 2 plus 1, or it's third order. And what we're doing is we are adding these exponents. All right, so there we go. Now we're going to question number 3, and we see that this is a hypothetical reaction of A, B, and C with the following orders. It says first order with regard to A. So we got to write a rate law that says it's first order with regard to A, zero order with regard to B, or first order and first order with regard to C. And so let's take a look at that real quick. Something happened to the computer there. All right, so we can write this as rate is equal to K, concentration of A, and put a 1, or you can not put a 1. You can put B to the 0, and you can put C to the 1. Or you could write it as rate is equal to K, A, C. All right, and that's because anything to the zero order is 1, and so it's not going to change anything. This would be a very valid rate law. But they're both very good. They're both very good. And so we want to get the overall order of the reaction. It's 1 plus 1. And let's do this. 1 plus 0 plus 1. That is equal to 2, or it is second order. And then what are the units of the rate proportionality constant K? Well, for second order, it's going to be 1 over molar times second, or you could express it as molar to the -1 times seconds to the -1. And then by what factor does the rate change when all reactants are triple? So if we have the rate and we apply our rate law is equal to K, and we're going to use our second one over here, K, A, C, and we say, okay, well, let's just say K is constant, and so we just plug in ones for the concentration of A and C. Well, then the rate is going to be equal to, let's say, 1 molar per second. And we could even say K is 1, just for simplicity. 1 times 1 times 1, it is going to be 1 molar per second. Now, if we look at this and we see, okay, rate is equal to K, A, C, and we do the same thing, K is going to be equal to 1, but now the concentration of A has increased 3 times, and the concentration of C has increased 3 times. Now we are at 9 molar per second. And so 9 over 1 it increases by 9 times. All right, so rate increases by a factor of 9. All right, and there we go. And that takes us all the way through the end. Hopefully that was helpful. Please like and subscribe. And once again, thank you for watching.